Hello, welcome back to our course on Advanced Quantum Theory. This is lecture 19. Let's remember how we arrived at the conclusion that the predictions of quantum theory must be probabilistic. The argument went like this. We noticed that in general, for an arbitrary observable, f, the expectation value taken to the nth power is not the same as if we take first the operator, take it to the nth power, and then calculate the expectation value. And this mismatch was visible, for example, in the difference when n is equal to 2. In particular, for n equal 2, we had that the difference, which is called the variance, which is the expectation value of f squared minus the expectation value of f squared, is generally generically. Let me explain how the word generically is usually used in physics, in case you haven't encountered it much yet. Generically means almost always. Mathematicians would say almost always, physicists say generically. Generically means that unless if you tune things in a very special way, then you have the generic case. So there are special cases and there are generic cases. So in particular, we have that the variance is non-vanishing, usually. If you take an arbitrary observable and you pick some arbitrary state, the variance is going to be non-zero. And that means that you have a standard deviation. That means you have a spread in the outcomes of the measurements. Now, we discussed this as a static feature of quantum mechanics. Namely, if at a given time you want to measure an observable, it might have some uncertainty, or in general, it has some uncertainty attached to it. The prediction will be with variance. But now let us look at the dynamical impact of this. This also has or this mismatch, I should say. And by that, I mean this mismatch here. This mismatch also has a consequence for the dynamics. To see this, let's consider why? Well, consider a system with some Hamiltonian h hat, which is some polynomial in the x's and then the p's. Then, what is the dynamics? Then, in classical mechanics, the dynamics of x of t and p of t are given by, obey, I should say, obey x dot of t, time derivative of t, is equal to dh by dp, and p dot of t is minus dh by dx, which can also be written as, or which arises from the Hamilton equations. And the Hamilton equations are x dot of t is equal to Poisson bracket of x of t with the Hamiltonian of x of t up and p of t. And p dot of t equal to, let me drop the brackets of t, h of x and p. Okay. Now, in quantum mechanics, how do the equations of motion then look like? Well, then we have that x hat dot of t is equal to 1 over IH bar. And this is the usual Heisenberg equation of motion. X hat of t, I'm really telling you nothing new here, but it's an important point to remember. P hat dot of t is equal to 1 over IH bar commutator of P hat of t with H hat of X hat and P hat. And these arise from the Poisson, from the Hamilton equations again, from the Hamilton equation. Oh, my software just crashed. Okay, so the Heisenberg equations of motion arise from the Hamilton equations of motion, and the Hamilton equations of motion are, of course, that x hat dot is equal to Poisson bracket of x hat with h hat, and p hat dot equal to p hat Poisson bracket with h hat. So this means that, as we stressed, as we discussed at the beginning of the course, the equations of motion, the differential equations of motion for the classical x of t and p of t, and the quantum x hat of t and p hat of t are the same. Now, we knew that, but let us now ask question, are the equations of motion of the predictions x bar of t and p bar of t also the same? And the answer to that is generically not. Now, why is that? To see why, let's just do an example here. So, example, let's say system with Hamiltonian h hat equal to p hat squared divided by 2m, plus some constant and then x hat to the 4th power. This is a this is an anharmonic. This is an anharmonic oscillator. It's not harmonic because it's not x to the 2nd power, but x to the 4th power. Then, well, let's work out what the equations of motion are. Equations of motion. Well, classically and quantum mechanically, it's going to be the same. Namely, we obtain that x hat dot equal to the Poisson bracket of x hat with our Hamiltonian, which is p hat squared over 2m plus r x hat to the 4th. And this means if we work this out, we find that this is p hat divided by m. Why is that? Well, the Poisson bracket between x hat and p hat squared, we've worked out before. It's 2 p hat. And that gives us this term here. The Poisson bracket of x hat with x hat to the 4th vanishes because the Poisson bracket with x hat vanishes. And then by the distributive rule of the Poisson brackets, that works out this way. On the other hand, what is p hat dot? Well, p hat dot is then the Poisson bracket between p hat and p hat squared divided by 2m plus r x hat to the 4th. Oh, I should say this is some real number. Just like for the ordinary harmonic oscillator, it's just some constant. All right, so we need to work this out. And in order to work out what this Poisson bracket is, and we are really going back here to the very beginning of the course, you can just use the axioms. Well, first of all, the Poisson bracket between p hat and p hat squared is vanishing, of course. So we only need to know what the Poisson bracket is between p hat and r x hat to the 4th power. What are we going to use here? Well, we're going to use that the Poisson bracket between x hat and p hat is minus the Poisson bracket of p hat and x hat. And it is 1. And we use, sorry about this. And we use the distributive rule, which is that f hat, g hat, h hat is equal to g hat, Poisson bracket of f hat, h hat, plus Poisson bracket of f hat with g hat, h hat. For all f hat, g hat, h hat. And we use this rule multiple times. Namely, we can write the x to the 4th power as x times x to the 3rd power. So we have two factors here. G is x, and h is x to the 3rd. And then we can work this out. And then what we get is that everything is reduced by 1 power of x hat. Right? Because the x hat, p hat that we get over here, this is an x hat. We can choose this to, sorry, this is a p hat. And this we can choose to be, for example, x hat. And then this we choose to be x hat to the 3rd. Then we get a Poisson bracket between the p hat and the x hat, which is just a -1. That's coming up here, f hat, g hat, that's this one, right? So this is just a -1. And this now is the Poisson bracket between our p hat and, well, what is h? H is x hat to the 3rd. So what you see here is that the original Poisson bracket that we had to worry about became a Poisson bracket where this term is easier now because we only have here an x hat to the third power and no more Poisson brackets to work out. Notice that we have reduced the degree of the polynomial in the Hamiltonian by 1 here. But here too, we have p hat Poisson bracket with x hat to the third. Now, of course, in the next step, we will write x hat to the third as x hat times x hat squared. And then we pull the same trick. And again, we get a lower 1 degree lower term here, and we get a 1 degree lower term over there. And so we can boil down everything to a polynomial, which is 1 degree lower than what we had over here. If we do this, then what is the end result? I leave it up to you to work out what this is. Namely, we obtain, using this, we obtain that the Poisson bracket between p hat and x hat to the fourth is equal to p hat with x hat to the third, equal to, and then all those tricks that I mentioned. You may want to be familiar with these things for a possible exam. I'm not saying it comes up, but it might. And then equal to, the end result is that it is minus 4x hat to the third power. And therefore, we have the second equation of motion, namely that p hat dot, the time derivative of the momentum, is equal to minus 4r x hat to the third. Okay, so these are our equations of motion. That's the equation of motion for the momentum. And the equation of motion for the position is this one. X hat dot is p hat over m. So we have x hat dot equal to p hat divided by m. So this is in quantum mechanics for the non-harmonic oscillator. What are the corresponding equations of motion in classical mechanics? Well, p dot equal to minus 4r x to the third, and x dot equal to p divided by m. This is classical mechanics. Right? Because in classical mechanics, same Poisson brackets business. Nothing changes. So we have the exact same equations of motion. What we're interested in now is what are the expectation values doing? Are the predictions also following the equations of motion? Because remember this, the quantum mechanical equations of motion here are operator valued equations of motion. And ultimately, these p and x here in the classical case are directly measurable. These are operators. In order to boil them down to predictions, we have to apply, we have to turn them into expectation values in order to get predictions. So now choose a state, psi, and calculate x bar of t and p bar of t. How do we do this? Well, we take our equations of motion, d by dt of x hat of t equal to p hat divided by m, and then we just apply psi on the left, psi on the right, psi on the left, psi on the right. And now, what do we obtain? Well, this, the time derivative, we can pull in front of this here. So we obtain that this is equal to d by dt of psi x hat of t psi. And then we have equal to psi, and there's a 1 over m, psi p hat of t psi. I'm sometimes writing the of t and sometimes not. It's always understood that these guys are time dependent. So what we obtain is that x bar of t, that's this bracket here, d by dt of it, is equal to 1 over m p bar of t. Okay, matches equations of motion above. Right? Same thing as above. If you look at this here, it's this equation here, or that equation here. So the expectation values are behaving the exact same way as the operators do and as the classical variables do. But let's do the same thing now for the momentum. So now we have to calculate d by dt of p hat of t equal to minus 4r x hat of t to the third. This is the quantum mechanical equation of motion, and we apply psi as we did before, psi, and then we can pull this in front, so we obtain that d by dt. Right? What we use for this is that the psi don't depend on time, d by dt of psi p hat of t psi equal to, well, psi minus 4r x hat of t to the third power psi. And what do we get? We obtain that therefore d by dt of p of t bar, expectation value of the momentum, equal to minus 4r, and then it's x hat to the third power of t, and then taking the expectation value of that. You see, this is where things deviate. The expectation value of the position operator to the third power is generally not the same as the third power of the expectation value. This is not the same as x bar of t to the third power. If we had here on the right-hand side that it is the expectation value to the third power, well, then we could justifiably say that not only are the operator equations of motion of quantum mechanics matching the classical equations of motion, but also the equations of motion of the expectation values of the predictions would match, but they don't. Okay, so we conclude that generally, because we just saw an example, and we notice, of course, that if this was not the fourth power here, but instead, see, if our Hamiltonian didn't have the fourth power, but the 400th power, or 293rd power, it would still be the same conclusion. The expectation values have non-classical behavior. So, therefore, expectation values, x bar of t, p bar of t, usually, or generically, let's use the term after all, generically, possess non-classical dynamics. Now, how different is it though? Or let's put it this way. When is it at least similar? When is it at least similar to classical? Well, it's similar. Well, let's look at the example. In our example, the issue was that x hat to the third power bar is generally not equal to x bar to the third power. Now, what is the problem, or is the source of the discrepancy? So when is this difference small? Now, the difference is small which is to say that x hat to the third bar is approximately x bar to the third, if delta x is small. You see, if delta x is small, then we have approximately an eigenvector of x. Or, let's put it differently, if delta x is small, then we can predict x with high accuracy. The numbers fluctuate very little. If delta x was tremendously small, for example, then we can pretty much predict what x is going to be. And that also means we can predict what x squared is going to be. And we can predict what x to the third is going to be, and what x to the fourth is going to be, and so on. So if the uncertainty in the offending variable, which is here x to the third, or x, if the uncertainty is small, which is to say the variance is small, which is to say that the second moment behaves normally, then also the higher moments, namely the differences between first taking the expectation value and then taking the power, is also small. So this means that as long as we are running our n-harmonic oscillator in such a way that the delta x is small, then we know that the expectation value is behaving approximately as if it was a classical n-harmonic oscillator. But of course, there is no guarantee that if you start out with a small delta x, that it will stay small. Generally, it might increase, and then this difference kicks in, and we have non-classical behavior. Generically, non-classical behavior is what you have. So this is the answer to the question, when is the dynamics of the expectation values at least similar to classical? Now, let's go all the way, and let's ask, under which circumstance is the dynamics of x bar of t and p bar of t the same, the exact same as in classical theory. That is to say, when do the quantum expectation values follow Newton's dynamics? And an answer can be given, and the examples are non-trivial. The answer is this. Assume that the Hamiltonian is a function of, and we can now do this also in greater generality, of x hat 1, x hat 2, x hat 3, p hat 1, p hat 2, p hat 3, and possibly more. If there are more than one particle, then you have more position operators, more momentum operators. So let's assume that this Hamiltonian is a polynomial in the x hat I and p hat j. So I runs through all values and j runs through all values of degree at most 2. So let's make the assumption that this is a polynomial which contains terms such as p1 squared, p2 squared, p3 squared. We certainly want that because we want to have p1 squared divided by 2m, p2 squared divided by 2m, etc. And the Hamiltonian is also allowed to have x squared terms, and it is allowed to have xp terms and px terms and x2, x3 terms and p1, x3 terms and so on. Just nothing higher than second powers. So at most 2 of these operators can be multiplied. So for example, the term x3p1 is already of degree 2. Can't multiply it with anything else in order to meet the assumption of this observation here. So let's assume that the Hamiltonian is a polynomial of degree at most 2 of all these variables here. Then we have that x hat dot, which is, if you remember, let's say I, is x hat I, Poisson bracket with h hat, is a polynomial of degree 1, which is to say, well, is linear. Let's just spell it out. Is linear in the xi hat and p hat j. And of course, same way, p hat j equal to Poisson bracket of p hat j with h hat is also linear. It's also a polynomial of degree 1 in the x hat I and p hat j. To be completely accurate, I shouldn't say linear, I should say affine, because it's allowed to have linear terms in here, but there could also be a constant. So let me write it out. So i.e., so this would really be affine. It's just that mathematicians would call it affine, physicists usually don't care and will call it linear even if there's a constant term. So what we have then is that if the Hamiltonian is of this simple form, that it is a polynomial of at most degree 2, then we have that x hat dot n is equal to sum over m, and then some coefficients, let's call it b and m, which are real valued fixed numbers, x hat m plus some coefficients, let's call them b tilde, n m p hat m plus possibly a number b check identity operator. And this is also a real number, and this is also a real number. And then similarly, we have that the p hat dot n is equal to sum over m. And then we have c and m x hat m plus c tilde n m p hat m plus some c check 1. And these guys are all fixed real numbers that are inherited from the coefficients of the Hamiltonian. And the point here is that because all of this here on the right-hand side is linear in x and linear in p, we have that the equations of motion, therefore, of the expectation values are the same classically as quantum mechanically. So therefore, we also have that x bar n dot equal to sum over m, and then b n m, and then the x bar m plus b tilde n m p bar m plus b, and p bar dot equal to sum over m c n m x bar m plus c tilde n m p bar plus c check. Right. And these equations are the same equations as classical. So what saved us here is that we had to take the expectation values here. You know, really, I should have put a psi to the left, a psi to the right, and, well, it's trivial, right? So if we have here psi x hat psi, then this is simply x bar. And we never have to take any higher powers of x or any higher powers of p. So therefore, the issue of non-trivial moment mismatch doesn't come up. Okay, so what we've shown is that for these Hamiltonians that are containing all sorts of degrees of freedom of arbitrarily many particles, but nothing with a degree higher than 2, have the feature that the expectation values obey the same equations of motion quantum mechanically as classically. So what kind of systems are these? What kinds of systems are these? Well, let's look at it. If the Hamiltonian is at most quadratic and the x and the p's, then what can we write down? Well, we can write down free particles, and we can write down harmonic oscillators, and we can write down any kind of coupling between these free particles and harmonic oscillators. And by free particle, I mean particles that don't have a potential. So what kind of systems are these? Well, free particles and harmonic oscillators. That are coupled. And that, of course, occurs a lot because harmonic oscillators are generally a very good approximation to systems close to an energetic ground state. So this comes up quite a lot. Now, what advantage does it have when we notice that this is the case? So advantages when working with such systems. Well, obviously, much easier to calculate. Certain certain predictions. And not only for the x bar and of t and p bar of t, but also other quantities, but also other quantities, such as xp minus, such as, let's just say, x hat squared bar, etc., and various other things, especially if the system is in a thermal type environment. Now, what exactly that means, we will find out later in this course. But let me just mention very briefly what this is about. Remember that the state of a quantum system is very important. And when we know the state of the quantum system, then we can calculate its time evolution. But imagine that you have a system which is immersed in an environment that has a certain temperature. And by immersed, I mean it's interacting with that environment. In that case, our system is continuously being bumped by the environment. And that means we quickly lose track of what state the system is in. And we can only assign probabilities to what state the system might be in. And if the system is in an environment that has a certain temperature, then we know that statistics. In these circumstances, having a Hamiltonian of that form that we deal with here makes things very simple. And of course, that situation occurs quite a bit. Harmonic oscillators in some environment that is at a certain temperature, that comes up quite easily. So it's an advantage then that we can calculate in this way more easily. And you can look this up under C keyword Gaussian quantum mechanics. Gaussian quantum mechanics is just ordinary quantum mechanics in the special case where the Hamiltonians are of degree at most 2 and the states of the system are of a particular simple form that are called Gaussian states. Now, I listed advantages. I should also list disadvantages. What are the disadvantages when we are working with such a system? Well, if we're working with such a system, a Gaussian system with Gaussian states and Gaussian Hamiltonians, then the disadvantage is that, e.g., for example, in a quantum computer, we would access less, strictly less than the true computational power of quantum mechanics. Some research, therefore, in the past few years has been about the following issue. The idea is to work with systems and states that are Gaussian and therefore reap the benefit of being able to calculate things much more easily than for generic quantum systems. and therefore, in principle, paying the price of not being able to build powerful quantum computers, except the idea is that we deviate a little bit from that so-called Gaussian behavior. And then when we do that, we can retain some of the computational ease, but we may open up much more computational power. Now, I don't want to leave you with the impression that these harmonic systems have sort of just trivial behavior, because obviously that's not true. So, caution. These harmonic systems or Gaussian systems have also very non-trivial quantum behavior. In spite of the fact that they're easy to calculate with. And for example, e.g., simple harmonic oscillator, p hat squared over 2m plus m omega squared half x hat squared. In this case, recall that h hat en equal to en, where the en are the eigenbases of the Hamiltonian being self-adjoint, the en form the eigenbases. It's a purely point spectrum, so all of the en value, the eigenvalues are discrete. And what are the eigenvalues? Well, we have that E naught is 1/2 h bar omega. E1 is 3/2 h bar omega. And then E2 is 5/2 h bar omega, and etc. That's the spectrum. It goes on to infinity this way. But what I want to draw your attention to is the fact that the lowest energy state has energy 1/2 h bar omega. This is very much quantum and not classical, because let us look at what this looks like classically. Classically, we have here the paraboloid, the parabola of 1/2 m omega squared x squared. Sorry, this is, yeah, that's right. So that's the potential here. And then if we have a classical harmonic oscillator, then we have a particle here that can be rolling up and down the potential, but the ground state, the lowest energy state for the classical particle is that it sits here right at the bottom. It sits here right at the bottom. And so classical lowest energy state, energy is 0. But quantum, the lowest energy, is equal to h bar omega half. What's up with that? Now remember that the ground state wave function of our harmonic oscillator in the position representation looks like this. It's a Gaussian, which means that the particle is likely to be found close to 0 and less likely to be found far away from 0. But it's not certain to be found at 0. The particle is most likely somewhere here. But what that means is that the particle is typically somewhere up the potential, right? Because it spends very little time at the bottom. I mean, yeah, it's the highest probability that it's here, but that's just one point, and very likely it's either to the right or to the left, and therefore its potential is elevated. And when you calculate what the expectation value of the potential is, given that it has this distribution in space, you find that the expectation value of the energy in the ground state is h bar omega half, exactly for that reason, because of the uncertainty in the position, the spread of the Gaussian wave function in the ground state. Because of that, the particle is in the ground state experiencing the potential not only at its lowest point, but also some way out. That's why the energy is elevated. So this is because delta x is larger 0 for ground state, right? That means that the particle is jumping around in here and experiencing the potential at values larger than its lowest value. That's what elevated the ground state energy from 0 to h bar omega half. This is general. This is general. Quantum systems usually possess let me reformulate it. The energy of the ground state of generic quantum systems is elevated compared to the classical system. And why do I say that? Well, because this argument for why the ground state energy of the harmonic oscillator is elevated did not rely on this parabola to be exactly a parabola. If this was an x to the 4th power, it would still be true. Clearly, this wouldn't be h bar omega half then. It wouldn't have to be that. Then the particle in its ground state would experience the potential somewhat differently because it leaks a bit more, a bit less to the left and to the right, and experiences therefore the potential on average differently. But it's always true that the ground state is going to be spread out. The ground state never has delta x equal to 0. So it's spread out and therefore always experiences the potential also left and right of the true minimum, and therefore the expectation value of the energy is elevated. Now, strangely, this leads us to one of the biggest mysteries of modern physics. Mystery. The mystery is this. I shouldn't put an exclamation mark because what we just said is not a mystery. What is now coming is a mystery. Quantum fields consist of harmonic oscillators. Now, quantum fields consist of harmonic oscillators because, you know, waves behave like sine and cosine, solutions to harmonic oscillators. And if you actually go into the math of quantum field theory, you find, yes, literally, the case that quantum fields consist of harmonic oscillators. Now, it doesn't mean that quantum fields can be solved by the methods that we just discussed. Quantum fields do not have Hamiltonians that are of this simple form that go only to the first and second powers of the fields in question. Right? For quantum fields, it's not the x and the p's. For the quantum fields, it's the phi fields and their canonically conjugate momentum fields. For quantum fields, we have more than the second power. So therefore, these are not of this simple quadratic kind. Instead, for quantum fields, they go up to the fourth power. So it's not the case that quantum fields have a behavior that, you know, the expectation value would have the same, the expectation values would have the same equations of motion as the classical fields would have. No, that's not the case. But still, this statement that we just made here should apply to quantum fields. Quantum fields consist of harmonic oscillators that are coupled non-harmonically. That are coupled non-harmonically. Namely, with up to the fourth power in the Hamiltonian. With all of this is not yet a mystery. Up to the fourth power in the Hamiltonian. So far so good, no mystery. The ground state is called the vacuum state. Now, its energy is elevated. Its energy, so the energy of the vacuum state, energy should be elevated. In fact, it should have, the quantum fields should have infinite vacuum energy density because we have to sum, for example, we have to sum infinitely many contributions of h power omega half. Well, plus interaction terms, plus the non-harmonic terms, but at least those, we have to sum those guys. But the experiment says, and the experiments show there is very little vacuum energy. Why? First, I should say, how do we know? How do we know? Well, energy gravitates. And vacuum energy gravitates. And yes, there is such a thing. It looks like there is vacuum energy, but it is about 122 orders of magnitude smaller than one might expect from quantum field theory. So, experiment. There may be vacuum energy So that is this elevation of the harmonic oscillator's ground state energy for all of the harmonic oscillators of all of the quantum fields. There may be vacuum energy, but it is about 122 orders of magnitude smaller than can possibly be expected from quantum field theory. What do I mean by can possibly be expected? Well, as I said, it ought to be infinite. Now, there are arguments that have to do, for example, with this generalized uncertainty principle that we covered recently. And there are arguments to show that actually it shouldn't be infinite. It should be a finite amount of vacuum energy. But the amount that you then predict is way too big, by about 122 orders of magnitude, then the amount bigger than the amount of vacuum energy that we see pushing the universe. In fact, vacuum energy, one can prove, affects the curvature of space-time, affects the curvature of the universe in such a way that it makes the universe expand. And it turns out that the universe is expanding at an accelerating rate. And the reason for that could be vacuum energy, because the regular energy in the mass of Earths and planets and suns and dust, that kind of energy makes the universe contract. It's only the vacuum energy that can make it expand faster and faster. Anyway, the conundrum I wanted to point you to is this. Whenever we have a harmonic oscillator, there is a very good reason for why the ground state of the harmonic oscillator has an elevated energy. And quantum fields consist of harmonic oscillators. And they all ought to have an elevated ground state energy, the ground state being the vacuum. So the vacuum should be full of energy. And what we observe is nowhere nearly as much vacuum energy as the theory would predict. This is the worst prediction of physics ever. We never got anything wrong by 122 orders of magnitude before. But yeah, well, we need creative young folks to figure out how that really works. Maybe one of you will figure it out one day. Okay, so that's as far as we got today.